Like other Smalltalks, we optimize certain special objects. So some objects, such as nil, true, false, are used so frequently that there is no reason to set up a separate space for it. And they're constants, you can't change them. So objects with this flag, 100, will then have space to identify whether it's nil, true, false. We can handle characters. So we have 61 bits left. And so, for example, single characters that would be in 8 bytes, or Unicode that would be in 16 bytes, 24 bytes, can fit into, 24 bits, 16 bits. 1, 2, 3 byte characters can fit into the object identifier. So we don't need separate memory space for characters, because they can just fit directly into the object pointer. Likewise, floating point numbers. We can store floating point numbers directly in the object ID, at least 61 bits of a floating point number. So that gives us a small double. We can also store integers within a 61-bit range. So we have assigned 61-bit 2's complement integer. So any number between -115, 2, so on, up to positive. So any number from -2 to the 60th through 2 to the 60th minus 1 can be stored directly in the object ID. We don't need to set up separate space in memory to hold integers as objects. They can just be handled directly. And if you get something smaller than this or larger than that, they're automatically converted to a large integer. So again, other Smalltalks are fairly similar in this sort of implementation efficiency. SmallDoubles is a 61-bit format based on the 64-bit IEEE format. There's a sign bit, 52-bit, significand, mantissa, coefficient, similar. So that gives us the identical precision to the IEEE. So we have exact precision. We have an 8-bit exponent instead of the 11 bits. So IEEE has a bit more very large and very small numbers. But if you need that extra large or small numbers, they can be converted to a real double instead of being stored directly in the object pointer. So this is again an efficiency, just so it takes up less space and can be compared and manipulated more easily. We have a few other objects. Nil is the sole instance of undefined object. That's stored directly in an object pointer. True and false are stored directly in the object pointer, so we don't have to go look them up. Characters from 0 to 2 to the 31st minus 1 are stored directly in the object pointer. Now, if we don't store it directly in the object pointer, then we actually have to have a real object somewhere, in memory or on disk. The real object has itself a structure that we'll discuss briefly. First is a 24-byte header. So 3 8-byte words are taken up with a header. After that, you can have 0, 1, 2 tag objects. This is something unique in GemStone. You can actually add instance variables, or you can add object references on an object-by-object basis. You don't have to change the class schema to add something. You can take any regular object and individually just add something else to it. We call those tags. And that's rarely used, but kind of makes for some interesting internal tools that you can build. Then, after that is instance variables. Instance variables are either named or numbered. Each object can have about 2,000 objects in its instance variables. named and numbered. So, for example, an array would have numbered instance variables, and you can create subclasses of collection that have both named and numbered instance variables. That's if it's an object collection, or an object type object. If it's a byte type object, then it simply is a sequence of bytes. Either a byte array or a string, for example, would be a good example. And there you have just numbered positions or instance variables. And there's a maximum of about 16,000 bytes in an object, in a byte object. Now, what does the header look like? Well, we mentioned it's 64 bits. The object ID is stored in the header, 40 bits. Then, of course, the 3 tag bits, which is going to be 001, since it's a true object reference. There's 64-bit of class and security. So 40 bits references the object ID of the class. So this way we know what class the object represents. Then there's a 16-bit security policy. Each object has a security policy with it that can identify the owner, the groups, and world permission. 64-bit size and flags. There's various lengths and flags. Is this a byte? Is it a class? Is it a invariant? We support invariant objects, which cannot be modified. There's a class identifier. Each object is described by one class. And the class tells us whether it's a pointer object or a byte object. The class tells us the named instance variables. Of course, it has to be a pointer to have named instance variables. The class tells us whether there are numbered instance variables. And that only works, that would be for a pointer type. If there's byte, if it's a byte object, then of course they're only numbered. The class tells us the superclass. And the class tells us the behavior. So messages that can be understood. So which messages can we understand? That is the method dictionary. Part of the header is a security policy. Each object is associated with a security policy. The default security policy is to allow world read and world write permission, which is essentially no security. But you can, in a security policy, have an owner and then permissions for world and group. You can identify authorizations for each of them, either read or write and or write and then none. So if you attempt to read an object for which you don't have security, then the virtual machine will throw an error. So security is right there built into the virtual machine level. You have a list of groups in the security policy that are also associated with the user. So each user can have one or more groups, and each security policy can have group, and then the default is world read. And then tag fields can have 2 object references, and then unnamed, these are unnamed instance variables unrelated to the class, and its space is used only if assigned. The tag does not add behavior.
Only instance variables.
This is only instance variables, yes. So this is not traits. This is not traits. This is not something that gives you that. The virtual machine simply holds onto this. You reference it by saying tag at 1, tag at 2, and at put. So just every object understands tag at put and tag at. So it's just an object that you can throw onto something that you can add to any object. So yeah, the tag fields, if you wanted to add, say, a dictionary, and then you could override does not understand and then look in the dictionary for keys and values or